All right, so we have our third and final video on the behavior of gases. So I just wanted to point out that this video is more about what we call fluid dynamics, which is essentially the study of how fluids move and why they move the way they do. It's a rather complicated field, so just keep in mind what we're talking about today is a very simplified version of all of this. Um, for a more complete discussion of fluid dynamics, you'd have to go into a much higher level mathematical course. So before we start, I want to remind you of two of the things we talked about in the previous video. So we talked about how if you compress a gas in a sealed container, the pressure will increase. And the second one was about fluids and how they always try to move towards areas of lower pressure. Okay, so the second one, an interesting application that we didn't get to talk about is just drinking through a straw. So we often use the phrase, that we suck the liquid up through the straw, but as I mentioned in the previous video, that's not really what happens. So when you're using a straw, what you're doing is you're expanding your lungs and you're breathing in essentially at first, which creates an area of low pressure inside your lungs. That causes the air in the straw to actually move into your lungs. Well, when that air leaves the straw, now you've created an area of low pressure in the straw, and that low pressure is less than the atmospheric pressure outside. Well, like I said, the atmospheric pressure is outside, so it's out here pushing down on the liquid. Well, if you have a pressure pushing down here that's greater than the pressure inside here pushing down, that liquid is naturally going to be pushed up. Okay, so that effect is that the atmosphere actually pushes the liquid into your mouth. It's not really that you sucked it in per se. So again, it doesn't really matter how you think of it. The idea works either way, but strictly speaking, that's what's happening. Okay, so moving on. One of the key issues with fluid dynamics is fluid pressure. We've talked about pressure in the other videos, but we haven't really defined it per se. Here's a technical definition. This at least could be one of the definitions: a measurement of the force per unit area on an object in the fluid or on the surface of a closed container. All right, well, when I read that definition, honestly, it doesn't really tell me anything. I don't find it very useful, so I'm not going to focus on this definition by any means. Well, some people, when they think of fluid pressure, they think of this, Bernoulli's equation. If you've never seen this equation before, don't panic. It's not something we're really going to use. It is quite complex in how it was derived and what it means, but it actually has a very simple interpretation that's really important for our discussion of fluid dynamics. So because we're a non-mathematical class, I won't go through this equation, but I'll try my best to give you a simple interpretation of how it's useful for us. So I'll start with the diagram here and try to connect the equation to the diagram. So first of all, on the right, you'll notice a lot of terms that have ones on them. So that's going to refer to this area here, where what this is imagine it's a pipe, okay, and then you have fluid flowing through the pipe. Okay, so V1 in this equation is just the flow velocity in this larger diameter section of the pipe. You could think of it as flow speed. P1 is simply the pressure inside the fluid here, the internal pressure. Okay. So on the right side, you have twos, terms with twos in them. So that's describing this lower diameter area. So V2 would be the speed or the velocity of the flow, and P2 would be the internal pressure at this point inside the fluid. So the simple way to interpret this equation is that when the velocity increases, okay, so that's what they're trying to show you here, is that V1 is the smaller arrow. When it goes to this lower or smaller area or smaller diameter, the flow increases. Okay, so Bernoulli's question essentially says that if V2 is greater than V1, the pressure at 2 will be less than the pressure at 1. That's essentially what this equation is telling us. Okay, so it's kind of summed up here. Increased fluid speed, decreased internal pressure. So to put that into a formal definition, a simple way to interpret that equation is that the faster a fluid moves, the less internal pressure there will be inside the fluid. Okay, this is commonly referred to as the Bernoulli effect. All right, so with all of these principles combined, we're now set up to answer this question. How does an airplane fly? Our aviation students, I'm sure, already know this, at least they should, if they're out there flying. But for the rest of us that don't, fly, we should spend a little bit of time to answer this question. So with anything nowadays, if you have a question, you Google it, right? Isn't that kind of how we get answers to our questions nowadays? So I thought I'd just try that. I went to Google and I typed in, how does an airplane fly? The fascinating thing is that the first few websites that popped up, that you have kind of ranking, and the top two or three websites that popped up all had pictures that looked like this, something like this. So the idea that they're trying to show you here is essentially Bernoulli's principle. So their claim is that the wing is shaped in a certain way so that the air that goes above the wing moves faster than the air that goes below the wing. So the Bernoulli principle says that if the air is going faster above than it is below, the pressure above will be less than the pressure below. So if we have less pressure above than we have below, there's an upward combination that gives us a lifting force. So they call that the lift on the wing. All right, well, this seems like a perfect application of Bernoulli's equation, and in some ways it is, but there's a big problem with this explanation. Have you ever seen an airplane fly upside down? Okay, let's go back to the original picture here. So an airplane is flying because there's an upward lift that's counteracting the downward pull of gravity. Okay, so if you have, let's see, we can draw this in here. So if you have an upward push that's equal and opposite to the downward pull of gravity, then you have zero net force in that vertical direction, which means you have zero acceleration, which means that you can just fly at a constant altitude. Okay, but going back to the upside down airplane, if we look at our picture here, well, the wing's now upside down. So if we flip that upside down, the shape hasn't changed. So if the shape hasn't changed, that means that the air below is going faster than the air above, which means that the pressure below is less than the pressure above, which means now we have a downward force. Well, combine that with the fact that gravity is pulling down. So now we have, let's see, now we have a downward force from the wings and a downward force from gravity. So that tells me that the net force is down, which means that the airplane should be doing that. Well, that doesn't actually happen. If you've never seen an airplane fly upside down, there's lots of videos that you can see that it does work. Okay, so the only explanation then is that by itself, this can't be the only thing that's happening. All right, so let's compare these pictures side by side. There's some common features in both pictures. All right, so first of all, look at the way this plane is kind of hanging in the air. Notice that the tail is much lower in this case. It's sort of got a downward angle, where here it's not so, and this isn't the exact same plane, but here you have a much more horizontal angle to the plane. I don't really want to focus on the plane itself. I want to focus on the wing though. So if you look at the end of the wing, you'll kind of notice that there is sort of an upward, it's not very good, but there's a slight upward tilt to the wing where the front of the wing is a little bit higher than the back of the wing. Okay, that same feature can be seen here. I'm not very good at using the mouse here, but you can kind of see an upward angle where the front of the wing is slightly higher than the back of the wing. Turns out that that's actually pretty important. Okay? So imagine I'm a little air molecule, right? And the airplane's flying through the air, so it's crashing into these molecules. It's literally bumping into the air. That's why it flies. So if I'm a little air molecule and the airplane's approaching me, when I hit that wing, I'm going to hit it, and because of its angle, I'm going to be deflected down. So if the air is being deflected down, that means that the wing is pushing essentially in a downward direction on the air. Newton's third law, that we've discussed quite a bit, says that if you have a downward force on the air from the wing, then there must be an equal and opposite reaction force, which means that the air is going to push the wing in an upward direction. Sorry. There we go. So looks like I draw about as good with a mouse as I do on the whiteboard. Anyway, so here the idea is that you'll get an equal as opposite Newton's third law reaction force. Okay, so that is a completely separate idea from the Bernoulli principle. This is essentially just a consequence of Newton's third law. If you're pushing the air down, the air is pushing you up. Okay, so when you Google how does an airplane fly, if you go down to the 5th or 6th explanation, you'll find better pictures that show things like this. All right, so our aviation students, I'm sure, are quite aware of this topic. So you notice the wing is now at an angle. So the angle of the wing relative to the wind, right there's your angle. So that's what they call the angle of attack. And it turns out that that's quite an important topic if you really want to know the details of how an airplane flies. All right, so putting it all together, again, this is kind of in some of the websites, like the 5th or 6th hit on my Google question. I think this is a better explanation that sort of combines all of that. So here you'll notice that at first the airplane splits the air. Okay, so the shape of the wing is important. So you're still going to get the speed increasing up here compared to down there. So Bernoulli's principle tells you that you're going to get less pressure up here compared to down there. So you're going to get an upward force from the air trying to get to that low pressure. Okay, there's another way you could think of it is the wing is also pushing the air out of the way. So if it's pushing the air out of the way, you're creating sort of a low pressure back here, which again adds to that idea of low pressure. And on the opposite, you're pushing the air out of the way, so you're sort of piling it up down here, so you're creating a higher pressure. So, you know, either way you think about it, with the airspeed increasing or the way the air is pushed around, you're creating lower pressure on top compared to the bottom. So you're getting that lift effect there. But if the velocity is increasing down the wing, then you must be accelerating down here as well. And if the air is pushing, like I talked about in the previous slides, if the air is pushing down on the air, accelerating it down, then there must be an upward push. So the combination of those two ideas is basically why we get lift on an airplane. So you can see it's not as simple as Bernoulli's equation by itself. There's also that concept of angle of attack, which is Newton's third law in application. All right, so I do want to emphasize something, though, that this explanation is rather simple in terms of how airplanes really fly. Okay, the full understanding of flight and fluid dynamics, it's pretty complicated. I mean, you have professionals that develop their whole career, you know, have aeronautic engineers to the study of this. So, you know, I don't want you to think this is everything you need to know, but it's a basic idea of what's happening. The interesting thing about understanding the airplane flight is it's actually the same explanation for why a frisbee flies. So if you Google how does a frisbee fly, and again, you ignore the first few hits on Google, surprise, the most popular hit isn't always the best explanation. But anyway, it's the same idea. So the shape, creates higher velocity, lower pressure on the top than the bottom, so you get that upward Bernoulli effect, but also the angle of attack, Newton's third law, pushing air down, which pushes the frisbee up. Okay, so pretty much the same idea either way. And that's it. All right, so guys, if you have any questions or I said something in any of these videos that doesn't make sense, feel free to let me know. Save your questions for when we get back together in class, and I'll happily spend some time to answer those. You can always email me as well. And I'll see you next week. Thanks, guys.